Now we'll discuss continuity and differentiability.
Why do we study continuity and differentiability? Now, most functions studied in mathematics, physics, and engineering, they vary continuously, or at least they're assumed so. Most real functions are continuous on practical scales, and thus, in our day-to-day life, our intuitive assumption is everything is continuous. We assume continuity very frequently without even realizing we are using it. Take, for instance, movies, which in reality are a series of still images running at a speed usually at a rate of 24 frames per second. But based on our immersive sensory stimulations, we take the movies or TV shows as continuous. We now know that energy, which was assumed continuous for a long time, is in fact quantized. Some modern theories even consider the quantization of space and time. At this point, no one knows for sure whether space-time is continuous or discrete. Even in our day-to-day life, we come across so many discontinuous functions and we deal with them without even realizing they're discontinuous. Say, for example, the acceleration of the car or the stock market fluctuation. So we are living in a world that is both continuous and discrete at different levels. The mathematical study of continuity was developed to comprehend the implications of unexpected jumps when the function is discontinuous. Over a while, a large set of theorems and tools were developed for continuous functions which have a broad application. Another important concept that is fundamental to calculus is differentiability. Differentiability as rate measure and slope of tangent leads to the concept of differentiation, which is crucial to almost all the applications of calculus. A class of differentiable functions is inherently distinct from the class of non-differentiable functions. Akin to continuous functions, many important theorems such as Rowley's theorem and mean value theorem are available for analysis of differentiable functions. Differentiability is a stronger requirement than continuity, which is needed for many results. Whether it is function in calculus or life per se, we have to deal with them when they are continuous and smooth, and also when they are discrete or sharp. Life and functions are a series of natural and spontaneous changes, and the ultimate human endeavor is to understand them, and that is why we study continuity and differentiability.
We'll begin our discussion with continuity at a point. Now, most of the functions, they are defined in their domain, which are generally intervals or union of disjoint intervals. So if we have to consider continuity of a point for such functions, we have to restrict ourselves in their domain. Now let us consider a function fx in the interval ab. Now in this interval, we will consider three kinds of points. First set of points are interior points. Now interior points are the points which lie in this open interval AB. So it consists of all the points x which lie in this open interval AB. So if we have this interval defined from A to B, this is x equal to A and this is x equal to B. So all the points in between A and B, they are interior points. Now, if a function is continuous at an interior point, say x naught, then this limit x tends to x naught, fx, it must be equal to fx naught. So this function fx will be continuous at this interior point x naught if this limit exists and it is equal to value of the function at that point. So it will be this f x naught. So in this case, all we need to do is we'll just need to find this limit and we must know this function value, and if both of them are equal, then we say this function is continuous at this point x naught. So basically in this case, this left hand limit f x naught negative must be equal to its right hand limit fx naught positive, and it must be equal to fx naught, and this value will be finite. So if we have to discuss the continuity of any function at a given point x naught, all we need to do is we have to write its left hand limit, which is limit x tends to x naught negative fx, which is L1, and then we'll find limit x tends to x naught positive fx, which is say L2, and we'll find this value fx naught, and it is L. Then this limit, it should finitely exist, and it should be equal to function value L. In continuity, most of the time you'll be asked to find continuity of a function at a given point or at a given interior point. Other type of points in this interval, they are left endpoints and right endpoints. So for this function fx defined in a to b, this x equal to a, it is a left endpoint, and x equal to b is a right endpoint. So this point where the interval starts, it's your left endpoint, and this point on the right, it is your right endpoint. Now if we say a function f is continuous at left endpoint a, so this function f is continuous at left endpoint x equal to a if limit x tends to a positive fx, it is equal to fa. So basically in this case, this right hand limit at a, it must be equal to this function value. So this is f a positive is equal to fa. Now if we look at this interval again, we have defined this interval from a to b. Now nothing is known about left hand neighborhood of a. So in this case, we'll restrict ourselves to this value at a and its limiting value in its right hand neighborhood. So here this function will be continuous at this endpoint a if fa positive equals fa, and if f is continuous at right endpoint, say x equals b. In this case, nothing is known about its right hand limit. Its left hand limit, which is limit x tends to b negative fx, it must be equal to function value at b. That is, left hand limit, it must be equal to function value, or fb negative must be equal to fb. So this is how we find continuity of function at the interior points as well as at the end points. Now if we consider graph of this function fx, which is a continuous function defined on this closed interval, say ab, this point is x equal to a, this point is x equal to b, and this point is x equal to x naught. Now this is an interior point. This is left end point, and this is a right end point. So if you look at this function, which is y equals fx at this point x naught, then its left hand limit, it approaches this point. Its right hand limit also, it approaches this point, and value of this function at this point, which is fx naught. So basically in this case, fx naught negative equals fx naught, and it will be equal to fx naught positive. That is, left hand limit is equal to function value, and it is equal to its right hand limit. And at this point, x equal to a, nothing can be said about its left hand limit, but if we look at its right hand limit, it's approaching this function value, which is fa. So in this case, this fa, it is equal to fa positive, that is, function value is equal to its right hand limit. And if we look at this point, which is b, nothing can be said about its right hand limit, but its left hand limit, it is approaching this value, which is fb. Now in this case, fb negative, it is equal to fb, that is, left hand limit is equal to function value. Let us take up an example. Say for example, we are given this function fx, which is defined as x into e to the power minus 1 upon mod x plus 1 by x when x is unequal to 0, and it is 0 when x is 0. Now it says, discuss the continuity of this function at x equals 0. Now in this case, this point x equal to 0, it is an interior point. So if the function is continuous, then f0 negative, it must be equal to f0 positive, and it must be equal to f0. So in this case, we have to find its left hand limit, its right hand limit, and its function value. So we'll start with its left hand limit. Its left hand limit will be limit x tends to 0 negative x e to the power minus 1 upon mod x plus 1 by x. Now we let x as 0 minus h. So it will be this limit h tends to 0 positive, and then it will be this minus h e to the power minus 1 upon mod of minus h plus 1 upon minus h, which is this limit h tends to 0 positive minus h e to the power minus 1 upon h minus 1 upon h. Now it will cancel. Now e to the power 0 is 1, and if we put h as 0, it will be 0. So in this case, this left hand limit, it is 0. So the value of f0 negative, it is 0. Now we'll find its right hand limit. For right hand limit, we'll write limit x tends to 0 positive x e to the power minus 1 upon mod x plus 1 upon x. Now here we'll let x as 0 plus h. So it will be this limit x tends to 0 positive h e to the power minus 1 upon mod h plus 1 upon h, which is this limit x tends to 0 positive h e to the power minus 2 upon h. Now by direct substitution, this is 0 and e to the power minus infinite is 0. So this limit is also 0. So its right hand limit f0 positive, it is 0. And the question, it says when x is 0, fx is 0. That means f0 is 0. So for this function fx, its left hand limit is equal to its right hand limit, and it is equal to its function value. That means it is continuous at x equal to 0. So we can say this function fx is continuous at x equal to 0. So this is how we find continuity of a function at a point. So basically what we have to do is we have to find left hand limit, right hand limit, which we have already studied in limits, and then we must know function value, which we can directly work out from the given function. Another type of questions in continuity are those where it'll be given that a function is continuous at a point and we have to find the value of some constants. Say for example, let fx be this function which is defined as 1 plus 1 plus mod sin x to the power a upon mod sin x when x lies between minus pi by 6 and 0. It is b when x equals 0 and it is e to the power 10 to x upon sin 3x when x lies between 0 to pi by 3. So it says find a and b if fx is continuous at x equal to 0. Now in this question, it is given that this function is continuous. So we have to find the value of a and b. And we know that this function will be continuous if its left hand limit at 0 will be equal to its right hand limit and will be equal to its function value. Now we'll find its left hand limit. Its left hand limit will be this f0 negative, which is this limit x tends to 0 negative 1 plus mod of sin x a upon mod sin x. Now we let x as 0 minus h. So it will be this limit h tends to 0 positive 1 plus mod of sin minus h to the power a upon mod of sin minus h. Now sin minus h is minus sin h, but there is this mod sin. So it will be mod sin h and mod sin h is sin h when h is 0 positive. So it will be this limit h tends to 0 positive 1 plus sin h to the power a upon sin h. Now first thing, we'll check its form. Sin 0 is 0, so this is 1 and a upon 0 is infinite. So it is 1 to the power infinite form. And if it is 1 to the power infinite form, we'll directly use this shortcut. So it will be this e to the power limit h tends to 0 gx, which is this power a upon sin h into fx minus 1, and fx minus 1 is sin h. Now this sin h and sin h will cancel. So this left hand limit, it is e to the power a. So from here we have our left hand limit f0 negative and it is e to the power a. Now we'll write its right hand limit, which is f0 positive and it is limit x tends to 0 positive e to the power 10 to x upon sin 3x. Now since exponential function is continuous, we'll take it in the power of e. So it will be e to the power this limit x tends to 0 positive, and we can write this as 10 to x upon 2x into 2x, and here we'll write this as sin 3x and we'll multiply and divide it with 3x. Now this x and x will cancel. Now when x tends to 0, 10x upon x, it is 1, and x tends to 0, sin x upon x is also 1. So value of this right hand limit, it is e to the power 2 by 3. So now we have left hand limit and right hand limit. So for this function, left hand limit is e to the power a and right hand limit is e to the power 2 by 3, and f0 in the question it is given that f0 is b. So this is b. So if we compare it, we'll get a as 2 by 3 and b as e to the power 2 by 3. And that is the answer to this question. Let us take another example, and this is, we have this function fx which is defined as under root x log x when x is greater than 0 and it is 0, when x equals 0. So basically this function fx, it is defined in the interval from 0 to infinite. And in this case, this point x equal to 0, it is left end point. Now the question says, discuss the continuity of this function f at this left end point x equals 0. Now for this question, this function fx is not defined in the left hand neighborhood of 0. So here we just have to check f0 positive and its value at 0. So first we'll calculate its right hand limit. Now f0 positive, it will be this limit x tends to 0 positive, and here this definition is under root x log x. Now first step is identify the form. This is 0 and log 0 is minus infinite. So it is 0 into infinite form, which is an indeterminate form. Now what we'll do is we'll write this as limit x tends to 0 positive log x upon 1 by under root x. Now this is minus infinity upon infinity form. Now if it is infinity upon infinity form, we can use L'Hopital's rule. So it will be this limit x tends to 0 positive, and this is 1 upon x, and here will be this 1 by 2 x to the power minus 3 by 2, which is this limit x tends to 0 positive minus 2 under root x, and if we put x as 0, it will be 0. So right hand limit for this function at x equal to 0 is 0. And it is given in the question f0 equals 0. So in this case, f0 positive, it is equal to f0, and it is equal to 0. That means this function fx is continuous at x equals 0. So this is how we check continuity at the endpoints. And if we take another example, suppose we have this function fx, which is greatest real function of x into sine x in the interval 0 to 1, and it says discuss continuity of fx at both the endpoints at x equal to 0 and at x equal to 1. Now this 0, it is left hand point. Here we just have to check its right hand limit and its function value. Now its right hand limit, it is limit x tends to 0 positive greatest integral function of x into sine x. Now when x is 0 positive, x lies between 0 and 1. It's a very small positive number, and when x lies between 0 and 1, value of greater function of x, it is 0. And also sine 0 is 0. So value of this right hand limit is 0. And if we find f0, now greater function of 0 is 0 and sine 0 is also 0. So in this case, f0 positive, it is equal to f0. Therefore, this function f, it is continuous at x equal to 0. Now we consider this right hand point x equal to 1. Here we have to find f1 negative and f1. Now its left hand limit at 1, it will be this limit x tends to 1 negative greatest integral function of x into sine x. Now 1 negative is some value which is little less than 1, and when the number lies between 0 and 1, its greater function will be 0. So it will be this 0 into sine 1 negative, which is finite, so it is 0. So in this case, left hand limit is 0, and if we find function value at 1, it will be greater function of 1 into sine 1, which is sine 1. Now in this case, f1 negative is not equal to f1, That means f is discontinuous at x equal to 1. So this is how we find continuity of function at interior points and at end points. Now, as we have done in limits, at times in continuity, we won't even find left-hand limit and right-hand limit separately. We'll just find limit of function and we'll compare it to the function value. Now, say for example, it says, let fx be this function sine e to the power x minus 2 minus 1 upon log x minus 1 when x is unequal to 2, and it says if fx is continuous at x equal to 2, find the value of f2. Now we know that if fx is continuous at x equal to 2, this f2, it should be equal to this limit x tends to 2 fx, which is this limit x tends to 2 sine e to the power x minus 2 minus 1 upon log x minus 1. Now limits, when we solve such limits, we don't take left hand limit and right hand limit because we know both the limits, they'll come out equal. So here we'll just find this limit. Now there are numerous ways to solve this. We'll solve it using substitution. We'll let x as 2 plus h. So it'll be this limit h tends to 0 sine e to the power h minus 1 upon log 1 plus h. Now if we put h as 0, e to the power 0 is 1. So this is sine 0, 0 and log 1, 0. 0 upon 0 form. Now we see three standard limits here. So we can write this as limit h tends to 0 sine e to the power h minus 1, and we'll multiply and divide everything with e to the power h minus 1. Now this is e to the power h minus 1. We'll multiply and divide everything with h, and then it'll be h log 1 plus h. Now this is standard limit sin x upon x. So it is 1. E to the power x minus 1 upon x. This is 1. And log 1 plus x upon x, it is also 1. So value of this limit is 1. So from here we can say value of f2 is 1. So in this case, we need not even find left hand limit and right limit separately. And if still you are not satisfied, then we know we have taken this as x equals 2 plus h. Now if we take h as 0 positive, it will become right limit. And if we take h as 0 negative, then it will become its left hand limit. 2 plus some positive value is 2 positive. So it will be this f2 positive. And if h is small negative number, it will become f2 negative. So for right hand limit, we'll take 0 positive, and for left hand, we'll take 0 negative. In either case, we'll end up having these three standard limits: sin x upon x, e to the power x minus 1 upon x, and x upon log 1 plus x. And all these three limits, they exist, and their left hand limit is same as their right hand limit. So for left hand limit, we'll get this answer as 1, and for right hand limit also, we'll get this answer as 1. So at times, we won't be even discussing one-side limits. We'll just take the limit and we'll put it equals to this function value. Like the question is, we are given three functions fx, gx and hx, and we have to find which of the following is or are true. Now a and b is hx is continuous or discontinuous at x equals 0. Now if we look at left hand limit at 0, it will be h 0 negative limit x tends to 0 negative, and when x is less than 0, it will be 1 by root 2, and then f of gx, and f of gx will be under root of 1 plus cos 2x minus under root of 1 minus cos 2x upon greatest interior function of cos 2x. Now this is limit x tends to 0 negative 1 by root 2. Now this is 2 cos square theta minus 1. So it will be this root 2 and then mod cos x and then minus, and this is root 2 mod sin x upon fractional part of cos 2x. Now we know that when x is less than 0, cos 2x will lie between 0 and 1. And if cos 2x lies between 0 and 1, fractional part of cos 2x will be simply cos 2x. Now first we'll check its form. So if we put x as 0, it will be this root 2 upon root 2, which is 1. So left hand limit of this function hx, it is 1. And if we find its right hand limit, h0 positive, will be this limit x tends to 0 positive, and it is fx. Fx is 1 plus x minus under root of 1 minus x upon fractional part of x. Now when x is 0 positive, fractional part of x is simply x. So it will be this limit x tends to 0 positive under root of 1 plus x minus under root of 1 minus x upon x. Now if we rationalize this, we can write this as limit x tends to 0 2x upon x into under root of 1 plus x plus under root of 1 minus x. Now x and x will cancel, so this value will be 1. h0 it is given as 1. So left limit is equal to right limit is equal to function value. That means hx is continuous at x equals 0. Now it says f of gx is an even function. Now if we look at this gx is defined only on the left neighborhood of 0. So we cannot ascertain f of gx, it is an even function because it is not defined on the right hand side of 0. So this option C is incorrect, and fx is an even function. Now if we find f minus x will be 1 minus x minus under root of 1 plus x upon fractional part of minus x. Now it will be equal to minus under root of 1 plus x minus under root of 1 minus x, and fractional part of minus x is 1 minus fractional part of x when x is not an integer. In the domain of fx, we do not have integers, but this is clearly not equal to fx or f minus x. So this function fx, it is not an even or odd function. That means this option D is also incorrect. So the only correct option is this option A. Now here the question is, we are given this function and it says, if fx is continuous at x equals 2, find the value of a and find the value of f2. Now what we'll do is, first we'll write its left hand limit. Now left hand limit will be limit x tends to 2 negative, and when x is less than 2, this is the definition. So this is e to the power x plus 2 log 4 whole to the power greatest integer function of x plus 1 divided by 4 minus 16 upon 4 to the power x minus 16. Now what we'll do is, we'll take this x plus 2 to the power of 4 and then e and log will cancel. So we can write this as limit x tends to 2 negative, and it will be e to the power log 4 to the power x plus 2 and whole to the power this greatest integer function of x plus 1 upon 4 minus 16 upon 4 to the power x minus 16. Now this e and log will cancel, and we also know that when x tends to 2 negative, greatest integer function of x, it is 1, as x is less than 2, and greater function of x, it doesn't take a limiting value, so we have to put the value of greater function of x. So now it will be this limit x tends to 2 negative 4 to the power of x plus 2 to the power of, now this is 1 plus 1, 2 upon 4 is 1 by 2 minus 16 upon 4 to the power x minus 16, which we can also write as limit x tends to 2 negative 4 to the power x plus 2 upon 2 minus 16 upon 4 to the power x minus 16. Now we'll solve this limit. Now first we'll check its form. If we put x is 2 negative, now this is 4 square 16, 16 minus 16 is 0. And this again is 4 square 16, 16 minus 16 is 0. So this is the 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So we can write this as limit x tends to 2 negative, and then this is 4 to the power x plus 2 by 2 log 4, and derivative of x by 2 is 1 by 2. And in the denominator will be 4 to the power x log 4. Now this log 4 will cancel. Now if we put x as 2, this is 4 square, which is 16 into 1 by 2, and here also it is 16. So value of this left hand limit is 1 by 2. Now we'll find its right hand limit. Now its right hand limit will be limit x tends to 2 positive. Now when x is greater than 2, this value is a into 1 minus cos x minus 2 upon x minus 2 10 x minus 2, which again is 0 upon 0 form. Now what we'll do is we'll multiply and divide this denominator with x minus 2. Now this is standard limit 10x upon x, which is 1, and this is 1 plus cos x upon x square, and it is 1 by 2. So this right hand limit will be 1 by 2. Now since this function is continuous at x equal to 2, then left hand limit, which is 1 by 2, must be equal to its right hand limit, and it must be equal to its function value at 2. So here value of a is 1 and value of f2 must be 1 by 2. Now here the questions. We are given this function fx, which is defined as this limit n tends to infinite cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n, which we will take common, and it will be this x minus 1. Now, if we find the value of f1, if x is 1, then x to the power 2n will be 1. So, in that case, this value will be cos pi minus, now this is 1 and this is sin 0. Sin 0 is 0, and here will be this 1 plus 0. So, value at x equals to 1 is minus 1. Now, if we look at its left hand limit, so it will be this f1 negative, which is limit x tends to 1 negative, limit n tends to infinite cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n into x minus 1. Now, x tends to 1 negative means value of x is less than 1. And if x is less than 1, then x to the power n is 0 as n tends to infinite. So, in this case, it will be this limit x tends to 1 negative, and it will be this cos pi x to the power n part will be 0 upon 1, and value of cos pi is minus 1. So, for this function, left hand limit is minus 1. Now, we will find its right hand limit. Now, right hand limit will be f1 positive, and will be this limit x tends to 1 positive, limit n tends to infinite. Now, this is cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n into x minus 1. Now, here x is greater than 1, and if x is greater than 1, then x to the power infinite is infinite. So, what we'll do in this case is we'll divide everything with x to the power 2n. So, if we put this limit, then we'll get this as limit x tends to 1 positive. Now cos pi x upon x to the power 2n ab0. So here we'll get minus sine x minus 1, and here also 1 upon x to the power 2n ab0. We'll get x minus 1. Now this is 0 upon 0 form, which is standard sin x upon x limit. So its value is minus 1. So for this function, left hand limit, it is equal to its right hand limit, and it is equal to its function value. So this function is continuous at x equals 1. And that's your option D. Now here the question is, we are given this function f which is continuous in R, and it says f 1 upon 4 to the power n, it is equal to sine e to the power n into e to the power minus n square plus n square upon n square plus 1. We need to find the value of f0. Now we know that as n approaches infinite, 4 to the power n approaches infinite, and 1 upon 4 to the power n, it approaches 0. So what we'll do is we'll take this limit n tends to infinite in both sides. So this is n tends to infinite f 1 upon 4 to the power n, and this is limit n tends to infinite sine e to the power n into e to the power minus n square plus this limit n tends to infinite n square upon n square plus 1. And the question says fx is a continuous function, and if it is continuous, then we can take this limit inside this function f. If this information was missing from the question, fx is continuous, we could not take this limit inside this function. Now since f is continuous, we'll take this limit inside, and we know that as n tends to infinite, 1 upon 4n tends to 0. So this is f0. Now here in this case, it will be this limit n tends to infinite. Now sine e to the power infinite is sine infinite, and sine infinite is oscillating value from minus 1 to plus 1, and this is e to the power minus infinite, and which is 0. Now 0 into anything finite is 0, plus in this case it is an infinite limit. Highest power of n in the numerator and in denominator is 2. So answer to this limit is coefficient of n square in the numerator upon coefficient of n square in the denominator. So from here we can say value of f0, it must be equal to 1, and that's your option B. In this question, value of f0 is 1, and also there is this one option that data is sufficient to find f0. So correct options are B and C. And the question is, if fx plus y is equal to fx into fy for all x, and fx is 1 plus gx into capital Gx, where this limit x tends to 0, gx is equal to 0, and this limit x tends to 0, gx, it exists, then prove that f is continuous at all x belongs to R. Now if we put x and y is both 0, we can write f0 is equal to f0 square. So from here either f0 is 0 or f0 is 1. Now if we put y as 0, fx into f0 is 0, which is a constant function. So for this, fx will be a constant function which is continuous for all x belongs to R. Now what if f0 is 1? So we'll take this case when value of f0 is 1. Now we'll check for continuity of fx at x equals 0. Now f0 negative, it will be 1 plus g0 negative into g0 negative. Now g0, it is 0, that means this f0 negative is 1, and f0 positive is 1 plus g0 positive and g0 positive. Now this again is 1. So that means this function fx is continuous at x equals 0. Now if fx is 0, then this limit, it cannot be 0. So we have to discard this possibility f0 equals 0. So the only condition that remains here is value of f0 must be 1. Now, once we know that f is continuous at 0, that is fh equals f minus h, and it is equal to f0, which is 1. We have to prove that it is continuous for all x belongs to R. Now we'll check for its continuity at any point x equals a. Now f a positive is f a plus h. Now it will be this f a into fh, and fh is simply 1, so it will be equal to fa. And the same way f a negative is f a minus h, which is f a into f minus h, and f minus h is again 1, so it is equal to fa. So for any point a, f a positive is equal to f a negative is equal to fa. That means this function f is continuous at all the points. Now here the question is, we are given two functions gx and fx, and then they have defined this function hx, which is mod of gfx. Now we need to find whether h is continuous or discontinuous at x equals 0. Now first we'll find its left hand limit. Now left hand limit will be limit x tends to 0 negative, so it will be this limit x tends to 0 negative mod of gfx. So value of x 0 negative will go into fx. Now if you look at this fx is greatest integral function of x upon greatest integral function of x plus 1, which we can also write as greatest integral function of x upon greatest integral function of x plus 1. Now if we put x as 0 negative, then in the denominator we'll have minus 1 plus 1, and there will be 0. So for this function fx, domain is defined from 0 to infinite union minus infinite to minus 1. So in the left neighborhood of 0, this function fx, it doesn't exist. That means this function g of fx will also not exist. So for this function hx, this left hand limit, it is not possible. Now if we look at its right hand limit, it will be h tends to 0 positive, and then it will be this limit x tends to 0 positive g fx. Now if x approaches 0 positive, then greatest integral function of x will be simply 0. So in this case, f0 positive will be exactly 0. We also have this fractional part x function here, but it won't make any difference. Now we are going to put value of f in this function g. So it will be this mod of tan inverse 0 minus cot inverse 0. Now tan inverse 0 is 0 and cot inverse 0 is pi by 2, and mod of minus pi by 2 is plus pi by 2. So right hand limit of this function is pi by 2. Now we'll find value of this function at 0. Now h0 is g of f0. Now f0 is clearly 0, so it will be this g0, and g0 is again tan inverse 0 minus cot inverse 0, which is pi by 2. So for this function gx, h0 equals h0 positive, and on the left hand side this function is not defined. So this function is continuous at x equal to 0. So the fundamental here is, if function is not defined on one side, then for continuity we are going to check either fa and fa positive, and if it is not defined on the right, then for continuity fa should be equal to fa negative. So answer to this question is this option A. Now here the question is, let fx plus y is equal to fx plus fy for all xy. And it says, if fx is continuous at x equals 0, then show that fx is continuous at all x. And that's our first question. Now, if we put x and y both 0, then we'll get f0 equals f0 plus f0. That means a value of f0 must be 0. So for this function, f0 is 0. Now it says fx is continuous at 0. And if fx is continuous at 0, that means f0 minus h must be equal to f0 plus h, and it will be equal to f0, and f0 in this case is 0. Now we need to show that it is continuous for all x. Now if we take any x belongs to R, then left hand limit at any x will be f x minus h. Now it is given that fx plus y is fx plus fy. So we can write this as fx plus f minus h. Now f minus h is f0, which is 0. So it will be equal to fx. And if we look at its right hand limit, which is fx plus h. Now fx plus h is fx plus fh. Again, this fh is 0. So this is also equal to fx. So for any real x, fx minus h will be equal to fx plus h, and it is equal to fx. That means this function is continuous for all x belongs to R. Now we'll solve this second question, which is if fx into y is fx into fy for all xy and fx is continuous at 1, then prove that fx is continuous for all x except x equals to 0, and we are given that f1 is unequal to 0. Now it says fx is continuous at x equals 1. Now that means f1 minus h will be equal to f1 plus h, and they'll be equal to f1, and none of it is equal to 0. Now if we look at any point A which is R except 0, then we can write left hand limit as limit h tends to 0 f a minus h. Now it will be this limit h tends to 0. Now we can write this as f, and if we take a common, it will be a into 1 minus h upon a. Now fx into y is fx into fy. So we'll write this as limit h tends to 0 fa into f1 minus h upon a. Now f1 minus h upon a is f1 negative, which is f1 minus h, and it will be equal to f1. So this is fa into f1. And the same way we want to write its right hand limit. Now right hand limit will be limit h tends to 0, and then it will be this f a plus h, which is this limit h tends to 0 f a into 1 plus h upon a, which again is fx into fy. So it is limit h tends to 0 fa into f1 plus h by a. Now this is f1 plus h, which is right hand limit at 1, which again is f1. So this is fa into f1. Now if we look at this function again, we are given that fxy equals fx into fy. Now if we put both x as 1 and y as 1, we can write f1 equals f1 square, which is the quadratic in f1. So from here we'll get this condition that either f1 is 0 or f1 is 1. Now f1 is unequal to 0, it is given in the question. So the only condition that we have here is value of f1 is 1. Now if we put f1 is 1, then this is fa and this is also fa. So for all the points a which are r minus 0, fa negative is equal to fa positive, and will be equal to fa. That means this function is continuous for all such a's. Now, what will happen at a equals 0? Now, at a equals 0, if we look at its left-hand limit will be limit h tends to 0, f minus h, which is f minus 1 into f0, and this f minus 1 may not be equal to 1. So at a equals 0, it may be continuous and it may be discontinuous. So it is not necessarily true. So this function is continuous for all x except at 0. And one counter example can be if we take this function fx as 1 upon x when x is equal to 0 and 0 at x equal to 0. Now this function, it satisfies all the conditions and it is continuous for all x belongs to r minus 0, and at 0 this function is discontinuous. Now here the question is, fx is defined for x greater than minus 1, and it says if f0 is 1 and f dash 0 is 0 and 1 plus fx into f double dash x, it is equal to 1 plus x, and if x is greater than 0, then f dash x is which of the following? Now if we look at f double dash x will be 1 plus x upon 1 plus fx. Now since this function has a continuous derivative and f double dash x exists, that means this 1 plus fx, it must not be equal to 0. So it will be either always positive or it will be always negative. That is given that at 0 this value is 1. So at 0 this value is positive. So that means this 1 plus fx, it will be greater than 0 for all x greater than 0. And this 1 plus x is also positive. That means f double dash x is greater than 0 whenever x is greater than 0. Now it implies that f dash x is an increasing function, and if x is greater than 0, then f dash x, it will be greater than f dash 0 as this function is increasing, and the value of f dash 0 is 0. So from here we can say value of f dash x is always greater than 0. That means f dash x is always positive, and that's your option A. Now here the question is, we are given this function fx, which is defined as greatest new function of x square minus greater function of x square. That is discontinuous at, we need to talk just at integer points. So let us say we are talking about x equals a, where a is an integer. Now if we look at its left hand limit, there will be this f a negative. We can write this as limit x tends to a negative, and this is greater function of x whole square minus greater function of x square. Now what we'll do is we'll let x as a minus h. So it will be this limit h tends to 0 positive, and here it will be greater function of a minus h square minus greatest greater function of a minus h whole square. Now greater function of a minus h is a minus 1. So it will be this a minus 1 whole square minus this limit h tends to 0, and here it is a square minus 2ah plus h square. Now h is nearly 0. So basically this h, it is greater than h square. So this minus term, it takes over. So this value will be little less than a square. So its greatest near function will be simply a square minus 1. Now if we simplify this, it will be a square plus 1 minus 2a minus a square plus 1. Now here a square will cancel. So it is simply 2 into 1 minus a. Now we'll find its right hand limit. Now for right hand limit, it will be f a positive, and we'll let x as a plus h. So we'll write it directly, limit h tends to 0 positive. Now this is a plus h square minus, and this is a plus h square greater function. Now get a function of a plus h square simply a square and then minus. This is limit h tends to 0 and it will be this a square plus 2ah plus h square. Now both h and h square, they are very small. So this is a square plus something. So its greatest real function will be simply a square. So we can write this as a square minus a square, which is 0. So for any integer, f a negative will be 2 into 1 minus a, and f a positive, it will be 0. And if we look at this f will also be 0. Now clearly they are equal if 2 into 1 minus a is equal to 0. That is, if a is equal to 1. So if a is 1, then they are continuous. And if a is unequal to 1, that means at all other integer points, they'll be discontinuous. So answer to this question is, it is discontinuous at all integers except 1, and that's your option D. Now here we are given this function fx, which is this summation r varies from 1 to n 10 x upon 2 to the power r into secant x upon 2 to the power of r minus 1 for all Rn belongs to n. What we'll do is, first we'll simplify this. Now if we let x upon 2 to the power r as theta, then x upon 2 to the power r minus 1 will be 2 theta. So first we'll simplify this, which is 10 theta into secant 2 theta. And what we'll do is, we'll write this as sin theta upon cos theta into cos 2 theta. Now we're going to write this sin theta as sin 2 theta minus theta upon cos theta cos 2 theta. This is sin a minus b, which is sin a cos b minus cos a sin b upon cos theta cos 2 theta. Now if we split this, we can write this as, this is 10 2 theta minus 10 theta. So we can write this function fx as this summation r varies from 1 to n, and 10 theta into secant 2 theta is 10 2 theta minus 10 theta. So it will be this 10 x upon 2 to the power of r minus 1 minus x upon 2 to the power of r. Now if we put values of r, we'll get this as 10x minus 10x by 2 plus 10x by 2 minus 10x by 2 square, and will continue up to 10x upon 2 to the power of n minus 1 minus 10x upon 2 to the power of n. Now all these terms, they'll cancel. So in the end, we'll have this fx as 10x minus 10x upon 2 to the power n. Now we can also write fx plus 10x upon 2 to the power n as 10x. So this is our first result. Now we are given this function gx, which is defined as limit n tends to infinite, and it will be this log fx plus 10x upon 2 to the power n minus fx plus 10x upon 2 to the power n whole to the power n into greatest function of sin 10x by 2 whole divided by 1 minus fx plus 10 x upon 2 to the power n whole to the power n. Now we know that fx plus 10 x upon 2 to the power n is nothing but 10x. So it will be this limit n tends to infinite log 10x minus 10x to the power n into sine 10x by 2 greatest real function upon 1 minus 10x to the power n when x is unequal to pi by 4 and gx is equal to k at pi by 4. That means f pi by 4 it is equal to k. Now it says find the value of k if fx is continuous at pi by 4. If we look at x tends to pi by 4, then x by 2 is pi by 8. Then this 10 x by 2 will be nearly root 2 minus 1 and sine of root 2 minus 1 it is not equal to 1. It will be less than 1. And if it is less than 1, then this greatest real function of sine 10x by 2 will be 0. So value of this greatest real function of x will be 0 when x approaches pi by 4. So we'll write this as gx equals limit x tends to pi by 4 limit n tends to infinite log 10x upon 1 minus 10 x to the power n. Now if we consider its limit at pi by 4 negative, it will be this limit x tends to pi by 4 negative, it will be this limit n tends to infinite log 10x upon 1 minus 10 x to the power n. Now when x is less than pi by 4, then 10x is less than 1. And if 10x is less than 1, then 10x to the power n will be 0 as n approaches infinite. So it will be this limit x tends to pi by 4 negative, and this is log 10 pi by 4, and which is log 1, that is 0. So left hand limit at pi by 4, it is 0. And if we look at right hand limit at pi by 4, right hand limit will be g pi by 4 positive, and it will be this limit x tends to pi by 4 positive limit n tends to infinite log 10x upon 1 minus 10 x to the power n. Now when x approaches pi by 4 positive, 10x is greater than 1, and in that case 10x to the power n will approach infinite, and anything finite upon infinite is 0. So in this case this function will actually be 0. So if gx is continuous at pi by 4, then in that case left limit must be equal to right limit, and it must be equal to value at pi by 4. We'll get the value of k as 0. So for this question, value of k is 0. Now it says also state points of discontinuity of gx in the interval 0 to pi by 4. Now in 0 to pi by 4, we know that gx is this limit n tends to infinite log 10x minus 10x to the power n greatest real function of sine 10x by 2 upon 1 plus 10x to the power n. Now in this interval 10x to the power n will be 0 as n tends to infinite. So this is 0 and this is 0. So in this interval, gx is simply log 10x. And since 10x is continuous in 0 to pi over 4 and log x is continuous when x is greater than 0, this log of 10x, it is continuous in x belongs to 0 to pi by 4, and there will be no point of discontinuity of gx in this interval. Now here the question is, we are given this function fx which is x cube minus x square minus 3x minus 1, and we are given hx as fx upon gx. What we will do is we will write this as x cube minus x square minus 2x minus x minus 1, and if we take x common, it will be x into x square minus x minus 2, and then minus x plus 1 which is x, and this is x plus 1 into x minus 2 minus x plus 1 which will be x plus 1 x square minus 2x minus 1. So that's our fx. Now it says this hx is continuous everywhere except when x is equal to minus 1. Now if it is continuous everywhere except at minus 1, that means this gx, it must contain one of the vector x plus 1, and then there will be some function hx which has no real root. Only then this function will be continuous everywhere except at x equals minus 1. Now it says limit x tends to infinite, hx is infinite. In part B it says limit x tends to infinite, fx upon gx, it is infinity. Though it is not given the question, but then gx, it has to be a polynomial function for this question. So I'll assume this gx, it is a polynomial function. Now if this limit is infinite, that means degree of fx, it must be strictly greater than degree of gx. Now degree of fx is 3, so degree of gx will be less than 3. Now we already know there is this one factor x plus 1, so degree of gx, it can be either 1 or 2. Now in C it says this limit x tends to minus 1, hx, it is 1 by 2. That means this limit x tends to minus 1, x plus 1, x square minus 2x minus 1 upon a x plus 1 hx, this value will be 1 by 2. Now this x plus 1 will cancel. Now from here we can say this degree of gx, it cannot be 2, because if it is 2, then in that case it will be a quadratic equation, and this quadratic equation will have two roots, alpha and beta. Now one of the root is minus 1. Now if we get second root which is not minus 1, then this function will be discontinuous at 2 points, minus 1 and beta. If we take this beta as minus 1, then in that case this limit, it won't be finite, it will be this infinite limit. So that means degree of gx can only be 1. So if degree of gx is 1, there is no hx in this expression. So from here we can say this limit x tends to minus 1, x square minus 2x minus 1 upon a, it must be equal to 1 by 2. Now if we put x as minus 1, it will be this 2 upon a equals 1 by 2. Value of a must be 4. So from here we get value of a as 4. And if a is 4, then this gx will be 4 x plus 1. So now we have gx, fx is already given, fx is x plus 1, x square minus 2x minus 1, and fx upon gx is hx. So this hx will be x square minus 2x minus 1 by 4. Now it says find the value of this limit x tends to 0, 3hx plus fx minus 2gx. So it will be equal to this 3h0 plus f0 minus 2g0. Now h0 is minus 1 by 4, so it will be this minus 3 by 4. Now f0 is minus 1 and then minus 2, and g0 is 4. So it will be this 9, 36. 36 minus 3 is minus 39 by 4. So value of this limit is minus 39 by 4.
Now here the question is, we are given this function fx, which is defined from 2n to 2n plus 1 and 2n minus 1 to 2n for all integers. If f is continuous, then which of the following holds for all n? Now first we'll look for continuity at 2n. At f2n, we have this equality sign. So f2n will be equal to f2n positive, and that is the definition. So it will be this an plus, and x here is 2n. So it will be this sign 2n pi. And if we look at f2n negative, here we have this definition. So it will be this bn plus cos 2n pi, and this function is continuous. So we'll equate them. So we'll get an. Now sine 2n pi is 0, and it is equal to bn, and plus cos 2n pi. Cos 2n pi is 1. So the first result that we have is an minus bn. It is equal to 1, and that's your option B. Now next we have to check its continuity at odd number. Now problem here is, here we have 2n minus 1 and 2n plus 1. So what we'll do is, in this first definition, we'll replace n with n minus 1. Then we can write this as an minus 1 plus sine pi x if x belongs to 2n minus 1 to 2n minus 1, and here it will be this bn plus cos pi x when x belongs to 2n minus 1 to 2n. Now we can write limits for 2n minus 1. So f 2n minus 1 negative, it will be equal to f 2n minus 1. It will be this an minus 1 plus sine 2n minus 1 pi, and here for f 2n minus 1 positive, it will be this definition, which is bn plus cos 2n minus 1 pi. Now this is an minus 1. Now sine 2n minus 1 pi is 0. This is bn, and plus cos 2n minus 1 pi is cos pi, and which is minus 1. So it will be an minus 1 minus bn. It must be equal to minus 1, and that's your option D. So the answer to this question is options B and D.
Now we are given this function fx, and we need to find the value of f0 if f is continuous at x equals to 0. Now we'll multiply this x inside. We can write fx as 1 upon 1 plus x, and this is x upon 1 plus x into 1 plus 2x, and this is x upon 1 plus 2x into 1 plus 3x. It goes all the way up to infinite. Now this is 1 upon 1 plus x, and we'll split this using partial fraction. So it will be 1 upon 1 plus x minus 1 upon 1 plus 2x. In the same way, we can write this as 1 upon 1 plus 2x minus 1 upon 1 plus 3x up to infinite. Now all these terms, they'll cancel. We'll get this fx as 2 upon 1 plus x when x is unequal to 0, and when x is unequal to minus 1 by n. Now it says this function is continuous at x equal to 0. In that case, this limit x tends to 0 fx, it will be simply 2, and it must be equal to function value. So in this case, value at 0 must be 2. Now here the question is, we are given that gx equals this limit n tends to infinite x to the power n fx plus hx plus 1 divided by 2x to the power n plus 3x plus 3, and x is unequal to 1. And it also says g1 is this limit x tends to 1 sine square pi into 2 to the power x upon log secant pi into 2 to the power x. Now it says, if it is a continuous function at x equals 1, then find the value of 4g1 plus 2f1 minus h1, assuming fx and hx are continuous at h equals 1. Now what we'll do is, we'll first solve this limit, which is g1. Now if we put x as 1, this is sine 2 pi, and sine 2 pi is 0, and here will be the secant 2 pi, which is 1, and log 1 is 0. So this is 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So it will be this limit x tends to 1, and we can write this as 2 sine pi into 2 to the power x into cos pi into 2 to the power x, and then it will be this pi 2 to the power x log 2. And here in the denominator will be 1 upon secant pi 2 to the power x, and then secant x is secant x tan x pi 2 to the power x and 10 pi 2 to the power x, and then will be pi 2 to the power x log 2. Now secant function will cancel, this pi 2 to the power x log x will cancel. Now here sine and sine will also cancel, so it will be this limit x tends to 1 2 cos square pi into 2 to the power x. Now if we put x as 1, this is cos 2 pi, and cos 2 pi is 1. So answer to g1 is 2. So we have value of g1, and value of g1 is 2. Now we'll calculate left hand limit and right hand limit at x equals 1. Now if we write its left hand limit will be limit x tends to 1 negative gx, which is limit x tends to 1 negative, and will be this limit n tends to infinite x to the power n fx plus hx plus 1 upon 2x to the power n plus 3x plus 3. Now we know that as x tends to 1 negative, that is x is little less than 1, then as n tends to infinite x to the power n, it approaches 0. So this expression will be 0, and this expression also will be 0. So we can write this as limit x tends to 1 negative hx plus 1 upon 3x plus 3. Now we put this limit, this is h1 negative, and in the question it is given that fx and gx are continuous functions. So this is h1 plus 1 upon 6. So our left hand limit is g1 negative, and it will be h1 plus 1 by 6. Now we'll find our right hand limit. Now this right hand limit is limit x tends to 1 positive gx, and will be this limit x tends to 1 positive, and then limit n tends to infinite x to the power n fx plus hx plus 1 upon 2x to the power n plus 3x plus 3. Now when x approaches 1 positive, That means x is greater than 1. And if x is greater than 1, then as n approaches infinite, x to the power n also approaches infinite. So what we'll do is, we'll divide everything with x to the power n. And if we divide everything with x to the power n, we'll have hx plus 1 upon x to the power n and 3x plus 3 upon x to the power n. So it will be this limit x tends to 1 positive, limit n tends to infinite, fx plus hx plus 1 upon x to the power n divided by 2 plus 3x plus 3 upon x to the power n. Now as n tends to infinite, this expression will be 0 and will also be 0. So this right hand limit will be this limit x tends to 1 positive, fx by 2, which is f1 by 2 as fx is continuous. So the right hand limit of this function will be f1 by 2. Now once we have function value, left hand limit and right hand limit, then for condition of continuity, we know that all the three, they must be equal. So if we equate them, then we can write 2 equals h1 plus 1 by 6 and it is equal to f1 by 2. So from here, we'll get h1 is 11 and f1 is 4. So now we have the value of g1, h1 and f1. Now we need to find the value of 4g1 plus 2f1 minus h1. Now 4g1 is 2, f1 is 4 and minus h1 is 11. Now this is 16, 16 minus 11 is 5. So answer to this question is 5. Now here the question is, we are given this function fx and it says if f is continuous at x equal to 0, then find the value of a. Now if we find its right hand limit, then the right hand limit at 0 will be f0 positive and we can write this as limit x tends to 0 positive, and when x is greater than 0, that's the definition, a to the power sin x minus a to the power 10x upon 10x minus sin x. What we'll do is, we'll take minus a to the power sin x common. So if we take minus a to the power sin x common, then we can write this as limit x tends to 0 positive minus a to the power sin x, then it will be a to the power 10x minus sin x minus 1 upon 10x minus sin x. Now this is a to the power 0, which is 1, and this is a to the power x minus 1 upon x when x tends to 0, as 10x minus sin x is 0. So this is standard limit ln a and this is 1. So value of this limit will be minus ln a. So for this function, right hand limit is minus ln a. Now we will find its left hand limit. Now left hand limit is f0 negative and will be this limit x tends to 0 negative, and this is log 1 plus x square plus log 1 minus x plus x square upon secant x minus cos x. Now this is log m plus log n. So it will be log m into n, and this is a plus b into a minus b. So it will be a square minus b square. So I'll directly write this as limit x tends to 0 negative, and this is log m into n. Now this is a plus b, a minus b. So it will be 1 plus x square whole square minus x square, and we let this secant x as 1 upon cos x. So it will be 1 minus cos square x, which is sin square x into cos x. Now we simplify this, we can write this as limit x tends to 0 negative, and here it will be log 1 plus x to the power 4 plus x square upon sin square x and cos 0 is 1. Now log 1 is 0, sin 0 is 0, so it is 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So we'll write this as limit x tends to 0 negative. I'll be 1 upon 1 plus x to the power 4 plus x square into its derivative, which is 4x cubed plus 2x. And here it will be this 2 sin x into cos x. Now what we'll do is we'll multiply and divide everything with x. Now sin x upon x, it is 1, and here if we cancel this x, we'll get this as 4x square plus 2. Now we'll put the value of x as 0. Now this is 1, and here it will be 2 upon 2, and cos 0 is 1. So this left hand limit is 1. So once we have left hand limit and right hand limit, we can find the value of a. Now right hand limit is minus log a. So if we equate them, we'll get minus log a equals 1, or log a equals minus 1, that is a equals 1 upon e. So here the value of a is 1 by e. Now from here the story of gx begins. Now it says gx is log 2 minus x upon a into cot x minus a for x unequal to a unequal to 0, and a greater than 0. And it says if gx is continuous at x equals a, then show that g e to the power minus 1 is equal to minus e. Now basically a in this case is 1 upon e. So we can write this gx as log 2 minus ex into cot x minus 1 upon e when x is unequal to 1 upon e. Now if it is continuous at 1 upon e, then g1 upon e must be equal to this limit x tends to 1 upon e gx, and this gx is log 2 minus ex upon 10 x minus 1 upon e. Now if we put x as 1 upon e, this is log 1, which is 0, and here it is 10 0, so it is 0 upon 0 form. So again we'll use L'Hopital's rule. So it will be this limit x tends to 1 upon e, and here will be this 1 upon 2 minus ex into minus e, and this will be secant square x minus 1 upon e. Now we put x as 1 upon e, 2 minus 1 will be 1, so it will be this minus e, and here secant square 0 is 1. So from here we can say value of g1 upon e is minus e, which is what we need to prove in this question. Now here the question is, we are given this function fx, which is cosec 2x cosec 2 square x up to cosec 2 to the power nx, and gx is fx plus cot 2 to the power nx. Now here what we'll do is we'll add cot to the power 2nx and subtract cot to the power 2nx. Now first we'll simplify this. Cosec 2 to the power nx plus cot 2 to the power nx. Now we can add this as sin and cos. So it will be 1 plus cos 2 to the power nx upon sin 2 to the power nx. Now if we apply half angle formula, so it will be this 2 cos square 2 to the power n minus 1x minus 1 upon this is 2 sin 2 to the power n minus 1x into cos 2 to the power of n minus 1x. Now this 1 and 1 will cancel, this 2 will cancel, this cos will cancel once, so it will be equal to cot 2 to the power of n minus 1x. So now we have this as plus cot 2 to the power of n minus 1x, and the term previous to it, it is cosec 2 to the power of n minus 1x. Now again it will be this cosec 2 to the power n minus 1x into cot 2 to the power n minus 1x. Now here it will be cot 2 to the power of n minus 2x, and this series will keep generating itself till in the end we have cosec 2x plus cot 2x, and if we simplify this, then we'll simply get cot x. So that means our function fx, it is nothing but it is cot x minus cot 2 to the power of nx. Now if we take cot nx here, we can write fx plus cot 2 to the power nx is nothing but this is cot x. So basically our function gx is cot x when x belongs to 0 to pi by 2. Now we are given this function hx and it says find the value of p to make the function h continuous at x equals 0. Now first we'll find its right hand limit. So it will be this h 0 positive and it will be this limit x tends to 0 positive, and this is cos x to the power gx, and gx is cot x plus secant x to the power cosec x. Now cos 0 is 1 and cot 0 is infinite and secant 0 is 1 and cosec 0 is infinite. So both of them they are 0 to infinite forms. So what we'll do is we'll use the shortcut directly. So now we can write this as this e to the power limit x tends to 0 positive, and this is cot x log cos x, and plus it will be e to the power this limit x tends to 0 cosec x into log secant x. Now we can write this as e to the power limit x tends to 0 log cos x upon 10x, and plus this is e to the power limit x tends to 0 log secant x into sin x. Now both of them they are 0 upon 0 forms. So we can use L'Hopital's rule. So it will be this e to the power and then this limit x tends to 0. Now this is log x is 1 upon cos x and cos x is minus sin x. So it will be this, and derivative of 10x is secant square x. And plus e to the power this limit x tends to 0. Now this is 1 upon secant x into 10x will be this 10x, and then derivative of sin x is cos x. Now this is 10 0 0 secant 0 1. So this is e to the power 0 1, and here also it is e to the power 0 1. So its right hand limit is 2. Now we'll find its left hand limit. Now h0 negative is this limit x tends to 0 negative e to the power x plus e to the power minus x minus 2 cos x upon x sin x. What we'll do is we'll use series expansion here. So this is limit x tends to 0 negative. This is 1 plus x square upon 2. This is 1 minus x plus x square upon 2, and then minus 2, and this is 1 minus x square upon 2 whole divided by x, and this is x minus x cube upon factorial 3. Now here this 2 it will cancel. So here minimum power of x in the numerator is x square and the denominator is also x square. So answer to this limit is coefficient of x square. Now this is x square by 2, 1, and 1 plus 1 it is 2. So answer to this limit is 2. Now left hand limit is 2, right hand limit is 2. So this function will be continuous if the value of p is